So I've got about half an hour, so I'm going to tell you a little bit about sort of nano stuff. I can't tell you very much, but I'll try and give you some introduction and then a little bit of an example or two of some of the applications that we're trying to work on here in CRANN using nanomaterials to do things that are actually useful. So I'm going to tell you about nanomaterials and nanoscience, a little bit about research in my own group, and then one slide on working with industry, because I think as may have been mentioned, CRANN is all about working with industry. The remit is to take the research that's done here in Trinity and bring that to companies and work directly with the companies to try and create new products and ultimately jobs. It's not solely about knowledge creation, just research. It's really about the economy. Okay, so what is nanoscience? I mean, we hear a lot about this nowadays. There's a lot of hype, and I hope it's not just hype. I mean, nanoscience, it deals with the science of very, very small things. And to put an arbitrary definition on small, what this really means is things that have sizes of less than 100 nanometers, which is 100 millionths of a millimeter in any given direction. And these materials, these very small materials, are called nanomaterials. Something that we often hear about as well is nanotechnology. And what nanotechnology is, it's using these nanomaterials to make things that might be useful. And ultimately, for the government who's funding all of this, what this means, as I said, is products, the economy, and jobs. So why nano? I mean, Peter over here talks about very, very big things. So why would I be interested in very, very small things? Well, there are two reasons, and they sort of speak to different sort of cohorts of people. One reason would be that it's new. It's only in the last 20 years or so that scientists have learned how to control matter on these very, very small length scales. So it's the edge of science, and of course that's very, very, very interesting. But that's also useful for practical reasons. Matter in general, behave differently at small length scales. So when you make something very, very small, it can have properties that would differ quite dramatically from the bulk properties. And this can open up new applications. Now, an example is the so-called nano harp, or it would probably be better to call it a nano xylophone. So this is a sort of a harp that has been machined out of a block of silicon. So the silicon has been cut away to give the shape of a harp. And these so-called strings are just sort of rods of silicon, and they can actually be plucked and they vibrate. But you won't hear them vibrate, because these strings, simply because they're so much shorter than normal harp strings, vibrate about 1 million times more rapidly than the strings in a harp. And that size difference is, in this case, that frequency difference is simply because of the size. So this is all classical mechanics. There's nothing strange. There's no quantum mechanics here. This is all classical, but you get behavior that's very, very different from normal. But in many very, very small systems, you can also have quantum effects, which means you get very, very strange things. And some of these strange behaviors can be very, very useful for future devices. So how small is small? These length scales of less than 100 nanometers are very, very difficult for us to comprehend because they're just completely outside our ken. So how small is a nanometer? So the best way to illustrate this is to slowly go from our length scale to a nanometer and sort of try and see that progression. So a nanometer is a millionth it's a millionth of a millimeter. So let's go there in steps of 10. So if you look at this is a photo of just some leaves, oak leaves. And this picture, imagine it's about 10 centimeters across. What it's trying to portray is about 10 centimeters across. So let's focus in by a factor of 10, and let's look at what's in the red square. Can you see that little red square there? So let's look in there. So go down by a factor of 10. Now we're looking at something that's 1 centimeter across. And you start to see structure in the leaf, the veins that you could see here, but now we see them a bit more clearly. So let's go down by another factor of 10, and you start to see that this vein starts to really dominate the image, and now you can start to see structure within the green part of the leaf itself. And the size of that is 1 millimeter. So let's go down by another factor of 10, and you can see actually in that green bit there is additional structure that you can hardly see there. You see these sort of bubble type shapes. Go down further, This is 1/100th of a millimeter, and you see further structure, and these are actually the cells that make up the leaf. Let's go down even further, and you can see the cell nucleus. And this is about a micron, or 1,000th of a millimeter across. Let's go down further, and if you go in there by another factor of 10, you can see the chromatin, which is a sort of a compact arrangement of proteins and DNA. So it's a method of basically storing vast amounts of information in a very small space. And you go in further, and you can actually see the DNA strands themselves. And then you go in another factor of 10, and this is 1 millimeter, and that's the length scale of the bases that make up the DNA. And that's sort of getting down to the length scale of molecules. And you can't really go much further than that. So as you go through these 8 or 9 steps, you're going from our world at length scales that we perceive on a daily basis down into a completely different universe, really. So to put it another way, something that's on our length scale is, for example, a football. So we can sort of immediately see that a football is of a very, very different scale to the size of the planet as a whole. So it turns out that the Earth is about 10 to the 8 or 100 million times bigger than the football. And we can probably just about grasp that. But let's go the other way. 100 million times smaller than the football, and you get down to about 1 nanometer. And as we'll see, there are molecules, there are spherical molecules that are about that size. And these live in the nano world, and these are as different in size to a football as a football is to the size of the Earth. So this is really a huge, huge difference. So what I'm trying to really get across here is that nanoscience really deals with the very, very, very small. And nanomaterials are the smallest materials possible, the smallest materials that you will ever be able to have, because the size scale below that is the size scale of atoms, and atoms are not materials. So nanomaterials are the smallest things ever, the smallest materials ever. So let's look at some examples. So this is the football-like, but a bit smaller molecule. It's called carbon-60, rather imaginatively because it's made of 60 carbon atoms. You can also have nanoparticles that are of similar sizes, but that are made up of, I mean, this bears really no relation to carbon as we would see it in graphite and diamond. But this is a gold nanoparticle, which is just a very, very, very small chunk of gold. So this is a little bit different. This is just a piece of gold, like you might have in a ring, but it's just very, very much smaller. But it has properties different to normal gold because it's got so much surface. This is something that's like, a bit like carbon-60. It's a cylinder made solely of carbon. And it's like a sheet of carbon rolled into a cylinder, and this is called a carbon nanotube. And actually these things are about 1 nanometer in diameter, but they can be very, very long. The longest nanotubes ever grown were centimeters in length. And that would mean that if I had, say, a cylinder with the same length to diameter ratio as the longest carbon nanotube, and say it was that diameter, and I held it sort of like that, the other end would be somewhere around Manchester. So that gives you some sort of idea about how thin yet long these structures can be. There's another type of nanostructure, in this case probably a microstructure, which, as we saw with the HARP, is made, these things are sort of made, as we would say, bottom up. So you sort of synthesize them. But you can also cut away bits of bulk material to pattern structures. And this nano guitar or micro guitar isn't for anything. This was made to demonstrate the power we have over materials at these small scales. And of course, people really like to show off, and some things are more pointless than others. So again, I don't want to go to labor too much on this, but just to show you the range of sizes, the range of size of nanomaterials is actually very, very similar to the range of sizes we encounter in biomaterials. So smallest nanomaterials are about 1 nanometer wide, maybe some can be 10 nanometer wide, but they can have length up to millimeters, centimeters. So this is the same range of scales from DNA-based pairs to viruses to bacteria to pollen to hairs. And it's interesting because these things are actually quite complicated structures, and much more complicated than the nanostructures that we can make today, but we would hope in the future to be able to make really such complex things as biomaterials with the control that nature has. Now, one commonality between these nanomaterials I'm talking about and these natural materials is that they're all predominantly made of carbon. And that's not a coincidence, there's a reason for that. So carbon is really a fantastic element, and the reason for that is because of where it sits in the periodic table. So this is a very, very special position in the periodic table, and ultimately what it means is that carbon can bond in a number of ways that other atoms just can't. So for example, a carbon atom can bond to 4 other, in this case, hydrogen atoms to give, in this case, methane. Or you can have a double bond, which allows a carbon atom to bond to 3 other atoms, in this case, 2 hydrogens and an oxygen, to give this molecule is formaldehyde. Or you can have a carbon bonding with a triple bond to 2 other atoms, in this case, a nitrogen and a hydrogen, to give hydrogen cyanide. So this is a versatility that we don't see with other elements. And while these are small molecules, these sort of bonding schemes can actually be extended in space to fill space. So if you take a carbon and bond it to 4 other carbons and continue that pattern to fill space, you get diamond. If you take a carbon and bond it to 3 other carbons and continue that to fill a plane, and then you stack those planes on top of each other, you've got graphite. If you take the linear array of carbon, you can almost make chains of carbon atoms, but actually this is the closest people have ever got. And a lot of research went on in the 60s, 70s, and 80s to try and remove these iodines and get to linear chains of carbon, but it turns out that this material is a very, very powerful explosive. And the number of labs, mostly in the States, that have been demolished due to explosions associated with this molecule is really quite astounding. So they gave up. Okay, so let's look at the middle one. So this is graphite, and graphite is what we use in pencils. And graphite is an array of weakly bonded 2-dimensional sheets. You see these 2-dimensional arrangements of carbons? Each one of those 2-dimensional sheets is called a graphene nanosheet. And graphite is just these things stacked on top of each other. And for a long time, people had quite good theoretical reasons to believe that you could never separate an individual sheet of graphene from the graphite crystal. There were thermodynamic arguments that suggested that the minute you separate it from the crystal, it would actually fall apart. But there's a really good lesson here, and I think that can very simply be stated as don't believe everything the theoretical physicists tell you. Because in 2004, by simply rubbing pieces of graphite on surfaces and looking with microscopes to see what came off, people found that just like writing with a pencil, you can create graphene, individual monolayers of graphene. And actually the theory had been wrong. And for this, the Nobel Prize was awarded in 2010 for the discovery of graphene. Not just because this is a sort of new material that hadn't been discovered before, that happens all the time. The Nobel Prize was awarded because graphene has got a unique set of properties that are unlike any other material and actually are very, very surprising. And people think that graphene will fill applications from super-fast computers to high-strength composites. And part of the reason for this is that graphene has a list of superlatives. It's the most thermally conductive material known to man, the highest electromobility known to man, it's the strongest material known to man, the stiffest material known to man, the stretchiest material known to man. It could go on and on and on. So the other thing is that graphene has been called the mother of all carbon forms because by cutting out certain shaped bits of graphene, you can make all other types of carbon. If you cut out bits of graphene and stack them on top of each other, you've got graphite. If you take rectangles, or as my mother would have called them, oblongs of graphene and roll them up into a cylinder, you get carbon nanotubes. If you take sort of rather odd-shaped bits and roll them up, you can get spheres or C60 molecules. So people who work in graphene claim that it's the most fundamental form of nanoscale carbon. So where did this all start? Nanocarbon research really started in 1985, although there had been stuff going on before that, and it started with discovery of this molecule, carbon-60, that we've seen before. And it was actually discovered not here on Earth, but in space, and like helium in the sun, it was discovered spectroscopically, so looking at light coming from space. Now, this got a lot of people excited, and the Nobel Prize was awarded for this discovery. for no really good reason except to show that forms of ordered carbon beyond graphite and diamond were actually possible. And then in 1991, people were trying to make C60 in very, very large quantities, and in a machine that had been designed to make C60, microscopists found this stuff. It's not C60, but it's cylinders of carbon, and these things are called carbon nanotubes. So there was a lot of debate about their structure, and very quickly it was realized that you take a piece of graphene and you roll it up into a cylinder, you have a carbon nanotube. And the important point here is that there's more than one way to skin a cat. You can take that piece of chicken wire and you can roll it up one way and then unroll it and roll it at a different angle to form a cylinder with a similar diameter but with different structure. You can see these cylinders have been rolled differently, and the point is that depending on the way they're rolled up, they can be metals or semiconductors, the band gap can be tuned, so a lot of people thought that these materials would be ideal for future electronics. So you have to be able to make them in large quantities, and people realized very quickly that they could be grown by chemical vapor deposition by basically in a hot gaseous environment. You have catalyst particles, that's a metal catalyst, and if you get things right, the gas goes into the metal, it cracks, and carbon comes out in an ordered form to give nanotubes. And these things can now be made in very, very large quantities. This is what's known as a forest, and this is an arrangement of carbon nanotubes where they've all been grown vertically from the base. And these ones here are a millimeter or two high. You go and look in with the microscope, you can see that they're all standy-uppy nanotubes, and you go and look in a bit closer, and they are indeed hollow cylinders with one wall. So one of the reasons that these things are really interesting is they're very, very strong. So just to put things, these are log scales, plastics which we use every day, predominantly for structural applications, i.e. because of their strength, are down here. They're not very strong, and it doesn't take very much energy to break them. Metals are a bit better, but not dramatically so. Some plastics, when the polymer molecules are aligned in the form of fibers, are actually very, very strong and take a lot of energy to break. And in fact, nylon, which you find in clothes that you buy in Dunn stores, is actually, we don't think about this, but is actually a very, very advanced high-tech material. The fibers, the plastic fibers that you use and you find in synthetic clothing are much, much stronger than steel, both on an absolute value and on a strength per weight value. And we never think about that. A bit stronger, the strongest fiber ever made. This is the strongest fiber ever made in a research lab, and then 10 times stronger than that, you've got individual carbon nanotubes or individual graphene sheets. So to put this in context, a carbon nanotube or a sheet of graphene is about 50 times stronger than the strongest steel ever made and has a quarter of the density. So these really are phenomenal materials, and one might imagine that it should be possible to use them for something. So how do we use them? The problem is that these things are really, really, really small. So actually forming them into useful structures is really, really, really hard. So you have to find ways to do it. And actually the chemical engineers have known how to do this sort of thing for a long, long time. If you can take any material and dissolve it in a liquid, then there are processing technologies that can give you everything from fibers to films to composites to plastics, all sort of stuff. So the first thing has got to be dissolving things in a liquid. So if you can do that with nanomaterials, then you can get somewhere. So the simplest way to do this is actually adding ultrasound. So you take your nanomaterial, you add it into water, for example, a solvent, and you put, this is an ultrasonic probe. This is a bit like the thing that is used in hospitals to image babies, although I wouldn't recommend it. This is about 10,000 times more powerful and has a completely different frequency. But you can see that the liquid is going black, and the reason the liquid is going black is a very small amount of nanotubes was added. The ultrasound breaks up the nanotube powder and turns it into individual nanotubes that have been dispersed in the liquid. And as I said, that's what, if you can get that, then the chemical engineers can tell you how to make that into useful things. The problem is, if you do this with water, once you turn off the ultrasound, the nanotubes stick back together again and they fall down to the bottom, and you're no better off. Now it turns out that the solution is very, very simple. You just add a little bit of soap to the water. Now, a lot of work was done on this using very expensive surfactants, which is just a technical name for soap. One of our small contributions was that we showed that actually fairy liquid is just as effective as the most expensive surfactants at this process. And if you add a little bit of surfactant, the surfactant molecules coat the nanotubes and then they will stay dissolved in the water essentially forever. So then how do you use that to make something useful? Well, we're going to make use of the fact that nanotubes are the strongest material known to man. So we might imagine that if you push nanotubes into a plastic, because they're very, very strong, they'll make the plastic stronger. So how do you make a composite? Well, what we have here, this is very crude. This is in a lab actually next door. And you've a glass tube that you inject a solution of dissolved polymer through. So the polymer is flowing around in a circle, being pumped around. And into that flowing polymer, with a needle, you inject your nanotube solution. And if you do that, what happens is, this is my PhD student, my ex-PhD student, Karen Young, who is now a physics teacher. So, very good. If you inject the nanotubes in, they collapse to form a fiber which flows down the tube and can be collected on some high-tech mandrels, i.e. upturned test tubes. In the bottom of the, actually, when we did this first, I was working in America at the time, and we were working on a project that was funded to the tune of $5 million. And actually, we found that the best way to do this was with upturned test tubes. So it really does show you that money isn't everything. Anyway, so you get fibers, and when you take them out of the liquid and dry them, you get stuff that looks like black thread, and actually is made up of polymer with carbon nanotubes in it. You can just see the nanotubes sticking out. And this stuff, when you add nanotubes, the strength of it actually goes through the roof. The strength of steel would be about here in this case. So you can dramatically increase the strength of plastics towards steel. By tuning the process to make low diameter fibers, you can get fibers that are much, much stronger than steel. And actually, when adjusted for density, dramatically stronger than steel. So this is a very, very simple example of how you can, take some test tubes and a piece of pipe, and you can make plastics that are much, much stronger than steel. You could do this in your kitchen. And I think this is important because people think nanotechnology requires vast infrastructure and loads of big machines that cost a lot of money. Well, it can do, but the point is it doesn't have to. And the simpler and cheaper things are, the more chance that they can be transferred into industry. And that's obviously important. Okay, we can do the same thing with graphene. Graphene plus soap. We can make composites. These are composite films. You can increase the strength by adding graphene. You can double the strength by adding about 0.5% of graphene. But the question is, can you do this in an environment where it will be useful? So this is a fiber made of plastic with graphene in there. And the important point is that the plastic that we've put the graphene into is polyester. Now, polyester is a very important fiber, often used well in many things, but among other things for clothing. And actually, there are 170 million tons of polyester produced for thread every year. This is big business. So if you put graphene in there, you can actually triple the strength of polyester thread just by putting in 0.5% graphene. That's a tiny amount of graphene. And that means, if you think about it, if your thread is 3 times as strong with the graphene than without, that means for a given application, you only need 1/3 the mass of plastic. And given that a lot of plastic comes from oil, which we're running very, very short of, that has to be an important application. Okay, so finally, I don't know if you've been listening to the radio or seeing the papers, you might have heard of this. We do a lot of research in CRANN, a lot. But the minute something came out that was to do with beer, the media were all over it. Last week, this was in 5 newspapers and I was on the radio 3 times, not because of the research, because it was associated with beer. So how can we help the beer industry, which I'm sure we would all like to do if we could. Beer, as many of us will know, comes in glass bottles. And the reason for that is that beer is carbonated, and if the carbon dioxide leaks out, the flavour goes. You have to use glass bottles. I think many people in this room, well, some people in this room will remember when Coca-Cola and Fanta and things like that came in glass bottles. About, I don't know, 20 years ago, plastic bottles became common, and now you only see these things in plastic bottles. The reason that happened is because the taste of soft drinks is not sensitive to the amount of carbon dioxide present. But the taste of beer is very sensitive to the amount of carbon dioxide present. So if you put beer in a plastic bottle, it loses carbon dioxide, just leaks out through the side of the bottle, and the taste will be completely destroyed within only 2 weeks. So the shelf life of beer in plastic bottles is 2 weeks, and the industry wants it to be 26 weeks. So can nanoscience help to preserve the taste of beer in plastic bottles, which I think we can all agree is an important application. So what you can do is, graphene is a flat, very thin, flat platelet. If you put very thin, flat platelets into a piece of plastic, then when gas molecules like carbon dioxide, gas molecules can diffuse through most plastics very, very, very quickly. But when the gas molecule comes to the graphene platelet, it can't go through the graphene. The graphene is completely impermeable to all molecules. So if it's to go through, it has to go round. But because the graphene is so wide relative to its thickness, to go round is actually quite a long way. So for a molecule to go around all of these graphene platelets actually increases the distances it has to travel by a very, very, very huge factor. And that means it takes much, much longer for the gas to get out. Now, the gas will eventually get out, but it'll take, if you get things right, 26 weeks rather than 2 weeks. And this is actually, you might think this is a silly little application that, say, the brewer, in this case SABMiller, wants to increase their bottom line. But hold on a minute. A large brewing company like SABMiller or Heineken or any of the other big conglomerates sell over 1 million bottles of beer per day. Now, those bottles of beer have to be moved around the place because the economic model for brewing nowadays is big centralized breweries, and you ship the beer over long distances. Glass is dense. It's heavy. The amount of fuel that it takes to move all those beer bottles around per day is staggering. And it's not even the fuel use. The amount of CO2 that's produced moving just those beer bottles around is a very, very large amount. If you use plastic bottles, you'll reduce the mass per bottle by about a factor of 5. And when you're moving around 1 million bottles per beer company per day, that is a huge fuel saving and a huge CO2 saving. So the take-home message is that nanotechnology doesn't have to be hard. It can be quite simple, quite conceptually easy, and you can do it in the kitchen. But even that sort of stuff can have very, very large societal advantages. Okay, so I didn't do any of the research that I showed. I have a large team of people, so I have to give them their credit. And of course, it's paid for by the government, either here in Ireland or in Europe. So I have to thank them, and thank you guys for your attention.